Section 6.4, a special factoring rule. So if you recall from a previous chapter, we saw that when we multiplied certain special binomials, a pattern developed. So for example, when we had 3x plus 5 times 3x minus 5, when you multiply that out, we have 3x by 3x and 3x by negative 5. That would give you a 9x squared and a minus 15x. And then taking the plus 5 through, we'd have a plus 15x and a minus 25. Remember that these middle terms added up to 0. And so we were left with 9x squared minus 25, which we called the difference of squares, because the first term is the square of the 3x and the last term is the square of the 5, and there's a subtraction, a difference between them. And in fact, in general, a plus b times a minus b is a squared minus b squared. And so in chapter 5, we were going from left to right. We were multiplying. Now, we can think of it as a factoring rule. In general, for any real numbers, a and b, or expressions a and b, a squared minus b squared is the same as a plus b times a minus b. That's the factoring direction for the rule. So if we are asked to factor something that fits that form, a squared minus b squared, we can immediately write it as a plus b times a minus b. We don't have to go through any of the other methods that we've learned. So for example, if we are asked to factor x squared minus 49, we notice that, well, x squared is the perfect square of x, and 49 is the perfect square of 7. So this fits the a squared minus b squared format, and so we can factor this as x plus 7 times x minus 7. And of course, we can check this by multiplying it back out. Why don't you try the other one on the slide on your own? Y squared minus 100. Well, that's y squared minus 10 squared. So this can be written in factored form as y plus 10 times y minus 10. All right, 4x squared minus 81. Well, 4 is the perfect square of 2, so 4x squared is the perfect square of 2x. And 81 is the perfect square of 9. So this can be written as 2x plus 9 by 2x minus 9. All right, why don't you try the other two on this slide on your own? (49z squared minus 1). Well, 49z squared is the perfect square of 7z. And 1 is the perfect square of 1. So this can be written as 7z plus 1 by 7z minus 1. 25m squared plus 9. Well, 25m squared is the perfect square of 5m. And 9 is the perfect square of 3. Wait a second. That's not a difference, that's a sum. Now, when we have a situation like this, where we have a sum of squares, this is a prime polynomial. Okay? We cannot factor a sum of squares at this time. All right, a little bit more complicated to finish off the section. Let's say we were asked to factor 121a squared minus 64b squared. Well, let's see. 121a squared. 121 is the perfect square of 11, so 121a squared is the perfect square of 11a. And 64b squared is the perfect square of 8b. So we have a difference of squares, and we would factor it as 11a plus 8b by 11a minus 8b. 2r cubed s minus 18r s cubed. Now at first glance, it doesn't appear that it fits the pattern. However, if we recall that the first thing we should always think of when factoring is there a common factor, then we can see that we can do something with this. So first, notice that we have a greatest common factor of 2rs. So this can be written as 2rs by r squared minus 9s squared. Now, focusing on the binomial, that's r squared minus 3s squared. And so this can be factored completely as 2rs by r plus 3s. Sorry, I wrote an r squared instead of a 2rs. So we have 2rs by r plus 3s by r minus 3s.